calm down a minute Okay, let's get started. Okay, let me just before getting started, let me just do a quick show of hands. This homework is just about, I think, the longest homework we'll ever have in this course. Unfortunately, it always happens at the beginning of the semester, and it scares away a lot of the students. Uh, how many people took less than 5 hours to do it? Uh, between 5 and 10? Jeez, we have a really strong class. Okay, 10 and 15, and larger than 15. Yeah, in the past we've always had a lot more people in that range, so I'm pleasantly, I guess, surprised that a lot of you did it between 5 and 10. So it is one of the longest homeworks. So don't despair if it took you a long time to do it. Um, let's see. So pick up the solutions from here at the end of the class. It's only available in hard copy, and if you miss it, you can always go to Rosita to pick up the remaining hard copies. I guess Cindy at the end of the class, if you can take the remaining ones to her, and then she doesn't have to do it again. And also any homework any graded homework you don't pick up, it's always with Cindy. Next week there's another lab homework. There's another homework due next Friday, which is really a lab, and I think it's a lot more straightforward than homework number one. It's a MATLAB. You can do it in MATLAB. It has to do with phase-only reconstruction. And there's some additional, the reason I put it on the web is because you also have to download some additional files from the web to do it. And this will be on the class web page, I don't know, by the end of the day or something. Hopefully by the middle of the day, but latest end of the day. And Cindy, if you can just go to Rosita to make sure she makes those changes that I was talking about. So what I thought I would do today is wrap up the discussion on the problem of reconstruction from partial Fourier information, or actually partial signal information, and then move on to Z-transform, multidimensional Z-transform. By the way, the book is supposed to be in the bookstore now, like today. Did anybody check it out yesterday to see if it is there? Yeah. So yeah, please feel free to get it, check it out. I was informed that they're supposed to be in today. Okay. Any questions or comments before I get started? Okay. So what we talked about last time, what we talked about last time was really the uh, reconstruction of discrete time signal or discrete space signals from samples of the Fourier transform magnitude or samples of the Fourier transform phase. And in the process of doing that, we concluded that in general, unique reconstruction is a lot more well-conditioned and better behaved if you're dealing with phase-only reconstructions rather than magnitude-only reconstruction. And one of the reasons for that is that for most natural imagery, the signals have similar Fourier transform magnitude. And I showed you that the results of the experiment whereby you start with two signals and you apply the Fourier transform magnitude of the first signal to the Fourier transform phase of the second signal, and you take an inverse Fourier transform, and what you get is a lot more like the second signal than the first, indicating that the phase of the Fourier transform carries a lot more information. And intuitively, you would kind of expect that, because Fourier transform, if you think about it, is a decomposition into a series of sinusoids. And for natural images, that have edges, the way you construct an edge is by adding up a bunch of sinusoids at different frequencies, but at the correct phase, so they result in a transition from low to high. And so intuitively, that's why phase is very important in images and in image processing in general. In addition, many image processing algorithms are designed to be processed by filters that are linear phase. And what that means is that the phase of the frequency response of the filter has to be straight line. And again, the reason you have that is for the sinusoids to line up properly so that the edges are preserved as you process an image with a filter. So you'll come to this again and again in image processing, where you're requiring a linear phase kind of a behavior by your filters. Okay. So what I'm going to talk about today is really the dual to the problem of reconstruction from Fourier transform phase. In particular, I'm going to talk about reconstructing signals or multidimensional signals from one bit of space domain information. In other words, there's one level crossing, and I'll explain that in just a second, and I'll explain why that's a dual of reconstruction from Fourier transform phase. And then I will move on and talk about reconstruction of signals from multiple level crossings. And that's the end of our discussions on reconstruction, and then we'll move on to multidimensional Z transforms. Are there any questions and comments? Okay. For those of you who came late, please hand in your homework at the beginning of the class rather than at the end. And I'm happy to take it from you so you don't have to walk. There is a tendency, and it's universal among all students, to actually I did it when I was a student, to work on the homework during the lecture if it is due at the end of the lecture. So I always make it due at the beginning. Okay. Yeah, I did a great number of my problem sets as an undergraduate in the lecture. Okay, so let's move on. Let's talk. What do I mean by reconstruction from one bit of space domain information? So previously, reconstruction of MD stands for multidimensional signals from, I call it zero crossing. And I won't spend a lot of time on this, just a little bit, because we didn't wrap it up in last time's lecture. So last lecture, what we saw was if you get one bit of phase of the Fourier transform of the signal, then you can reconstruct it. Okay. Now, if you think about a space domain signal like this, let's call it X and Y. Let's say this is, suppose that you have um, a continuous time or continuous space two-dimensional signal. So this is a continuous space 2D signal. So this x and y are real variables. They're not integers. Okay. So you can think of it that if it has values sticking out of the paper. You can think of it as a mountain with valleys and ups and downs, etc. So I take a knife and I cut it at a fixed threshold, at a fixed height, and you can call that zero crossing, or you can call it a level crossing. Then you get a contour. So this contour represents what's called the level crossing of the signal. Okay, and what does it mean is that and it could be one contour, it could cut it at multiple places, etc. But what does it mean is that the points, this contour is telling us, it's essentially dividing this x and y into two regions. Points in the plane where you're above a threshold, and points on the plane where you're below that threshold. That's what that I mean, think of a set of range of mountains. I mean, and you just cut it with a plane, then certain points are above it and other points are below it, or vice versa. That uniquely tells you kind of the polarity of the points in this space. So from that point of view, it's very similar. That's why we call it the counterpart or the dual of the problem of one bit of phase, because in the Fourier transform, if you have the phase function and you quantize it to one bit, either between 0 to pi or pi to minus 2 pi, essentially you're defining the polarity of the Fourier transform as well. So for this reason, this is the dual of the problem reconstructing this two-dimensional continuous time signal from its one level crossing is dual to the problem of one bit of phase reconstruction this two-dimensional signal from one bit of phase of the Fourier transform.
When you say the Fourier transform is 2-bit and 1-bit, like, can it take on more than two values, or what does that mean really?
Repeat the question.
You said the Fourier transform is 1-bit, right? You change it to 1-bit and still.
One bit of phase.
What does that really mean? Like, what do you mean?
Okay, so if you have x of omega 1 and omega 2, right? Then it has a magnitude and it has a phase, right? An angle. The angle we call phase, phi of omega 1 and omega 2. And what we talked about last time is, as a function of omega 1 and omega 2, you have a repetitive function that goes from minus pi to plus pi, and you can plot phi of omega 1 and omega 2, right? And we can either reconstruct the signal, the phi of omega 1 and omega 2. I'm sorry, we can either so this corresponds to a discrete time signal, x of n1 and n2, right? So what we talked about last time was if you have samples of phi, you can get back x. And furthermore, I talked about if you take samples of phi and quantize those to one bit, positive, +1, -1. All right? That's what Patrick Van Hove and those guys showed. Even then, you can reconstruct x. And right? And we showed that the problem of reconstruction from phase is much more numerically stable, well-conditioned problem than reconstruction from Fourier transform magnitude. For one thing, you can apply it to large images and it converges with no problem. For another, you can introduce a lot of perturbation to the input by quantizing the phase to just one bit, and it still converges. Remember we talked about numerical analysis and well-conditionedness of the. Yeah. Yeah. Yeah, absolutely. That's what Patrick Van Hove showed. And I don't know if there's an example of that in the book, but there's the examples of big images could get reconstruction from this one bit of phase information. Okay, and your next lab, off the top of my head, I don't know if you quantize it to one. Do we? We don't. Your next lab talks about reconstruction from Fourier transform phase. So you get to play with that a little bit. But if you're extra curious, you can just quantize it and convince yourself that it still converges. Okay? So so that's what I mean. So here we're quantizing with one bit, and here we're quantizing this. We're constructing the level crossings. So so this one bit of phase of Fourier transform was done by Van Hove, this Belgian guy I was just talking about. And this other stuff, reconstruction, a continuous space, two-dimensional signals from its level crossings, was done by Curtis and Oppenheim. And this was around, I don't know, 1983 to 5. Sue Curtis was actually my office mate at MIT. And there's a funny story about her. She was a big baseball fan, and she used to play baseball, and she kept a bat in our office. And right around that time, like 1984, there was a grad student in math at Harvard who killed his advisor with a baseball bat because he had been a graduate student for 17 years. And so one day our advisor Oppenheim came to our office, and of course we had this couch that was just disintegrating. I mean, you would sit on it and it would just hit the ground and the fabric would come off. And he sat on it, and we were really surprised. Why is he visiting us, in this shabby office? And he said, suddenly his eyes looked at the bat. He said, "Whose bat is that?" And Sue said, "Oh, it's mine." And he quickly left the office. This was right around the week or the days where the guy had killed his advisor at Harvard with a bat. So, so anyway, yeah, I haven't kept track of Sue. I don't know where she worked at Lincoln Labs for a while, but I don't know where she is now. So her thesis, her PhD thesis, was just this, and I'm gonna just spend 2 minutes summarizing kind of an entire PhD thesis. And I mean, needless to say, when I go to my graduate student area office, I always look for objects like that too, just to make sure that my life is not in danger or anything. Okay, so here's what the formulation of what we have. So we're assuming that, so we're assuming that this f of x comma y, which is a continuous space signal, that means x and y are continuous values, is a band-limited periodic signal and can be written is BLP, which means band-limited, not BLT, not bacon, lettuce, and tomato, but BLP, band-limited and periodic. And you might, let me just write down the expression for it, and then you might think, oh, that's such a restrictive class of signals. Where on earth do I find a band-limited periodic signal? Well, it turns out that you can start with any signal, and by expanding in Fourier series coefficients, you can make it approximately periodic, so that's not a big deal. So let's write down the Fourier series expansion of it. Because it's band-limited and periodic, it has Fourier series expansion, not Fourier transform. So the Fourier series expansion would be the summation from k1 minus n to plus n and k2 minus n to plus n, f of k1 and k2, e to the j 2 pi k1x, e to the j 2 pi k2y. And so these are the Fourier series coefficients. Okay. And again, if you've got any signal, you can quickly make it band-limited and periodic by computing its DFT, and then that essentially periodicizes that. So the name of the game for coming up with this result, I mean, essentially what Sue Curtis showed is that zero crossings or one level crossings of this f of x comma y is enough to uniquely reconstruct it. And on the surface of it, you might say, that's impossible. You can't start with an image and with just one level crossing tell me what goes on. But the trick is that you need to know the reason that the result is intuitively counterintuitive is that you need to know the locations of that level crossings infinitely accurately. So yet another ill-conditioned problem, right? If you quantize it, or if you know it with finite precision, if you know it with not enough precision, you can't do it. You got to know it infinitely precisely. But let me tell you what the derivation of it is extremely elegant and straightforward, and it has to do with two-dimensional polynomial theory. Okay, so how can I make this a polynomial? I mean, this is by now this must be a really uh, obvious trick to you guys, in that you can say e to the j 2 pi x is one variable w, e to the j 2 pi y is another variable. So we do this change of variables. And now what I have is a two-dimensional polynomial. So f of x comma y is just becomes k1 minus n to plus n, k2 minus n to plus n, f of k1 and k2, w to the power of k1, z, another variable to the power of k2. And again, the fact that these indices goes from minus n to plus n, that's a minor detail. We can just multiply by a factor and shift them out and make it go from 0 to 2n. But this is really a polynomial of degree 2n in w and degree 2n in z. And you can even talk about, if you can roll up just a little bit, the region of support of powers of w and z. It goes 0 to 2n, 0 to 2n, and so this point has degree 4n if that's the way you count degrees, right? And the way Sue solved this problem was applying a theorem from algebraic geometry. Okay, it's called Bezout's theorem, and it goes like that. It says if you have two-dimensional polynomial of degree r and s, and what they mean by degree of a polynomial is the maximum degree in variable 1 and variable 2, right? Then at most they can have two-dimensional irreducible. It has to be irreducible again. You can already see the sources of numerical ill-conditionedness and popping all over. You know, the thing has got to be irreducible. We need to know the zero crossings to infinite precision. It's all bad signs. So if two-dimensional polynomials of degree r and s are both irreducible, then at most they have rs common zeros. Okay, and again, don't worry about the fact that we're talking about level crossing versus zero crossing, because if you have a regular signal, you can just shift it by a little bit to make its a constant level crossing to be a zero crossing. It's just a constant variation of it, so don't worry about it. Okay, so what does that mean? Well, it just means that if I sample, so in this case, my polynomial is of degree 4n, right? So what that means is that if the implications for this particular polynomial is if I sample this at 16n squared or more, then I've uniquely reconstructed this. Again, I'm assuming most images and correspond to have irreducible polynomials as their Z transform, as their Fourier transform, because we know that Monty-Hayes had shown that that's really the case, that the set of reducible ones are of measure 0 in the set of all polynomials. So that's the reason for this irreducible business here. So if you pick a random signal applying Bezout's theorem, then you can conclude that if you sample 16n squared or more zeros of f of x comma y, then applying Bezout would tell us that we can uniquely reconstruct it. And what does it mean, uniquely reconstruct it? That means we can uniquely determine f of k1 and k2. Okay. And as I said, the trick with this thing is that, and this degree, I hope you understand what I mean. It means the maximum degree in W and Z. So here the maximum degree is 2n, then 2n plus 1, all the way, but by the time I get here, it's degree 2n in one variable, 2n in the other variable, therefore the total degree is 4n. Okay. So is that argument clear? So two distinct polynomials, if they're both irreducible, can't have more than RS common zeros. So if you start with an image and you assume that it corresponds to an irreducible polynomial, and you sample it at 4n times 4n is 16n squared or more zeros, boom, you can uniquely reconstruct. And from a practical point of view, how would staring at this thing, how does one go about reconstructing f of k1 and k2? So essentially what I'm telling you is that we have the locations of these zeros here. I'm going to sample this as 16n squared. I start with a band limited periodic signal. I compute its zero crossings, or an arbitrary one level crossing, as 16n squared. And now, staring at this, what would be the algorithm that pops to your head most easily to recover these f guys? Make a guess. It's pretty straightforward. How does this f of k1 and k2 enter into this equation? In what fashion is it? Actually, if it is difficult for you to see, let's look at this thing here. This might be more of a giveaway. So essentially what I do is I sample f of x squared at its 16n squared zero crossings. And let's call those x naught comma y naught, x1 comma y1, x2 comma y2, all the way to x 16n squared comma y 16n squared. And if I plug that in, that means I have...
Question?
Yeah.
When you say zero crossing, I mean, do you just mean zeros of this polynomial in frequency space, right?
No. I'm talking about zeros of f of x comma y. I have expressed f as a polynomial. And the reason I have done that, because this is its Fourier series expansion. And what I showed you is that by doing this change of variable, it is now a polynomial in w and z. The reason I did that was to apply Bezout's theorem. But the upshot of the whole thing is what Sue Curtis showed, and applying Bezout's theorem, is that now if I sample f of x comma y at 16n squared values of its zero crossing, f of x comma y is a picture, is an image. In fact, this morning before coming here, I tried to print Sue's paper, but I think because of the internet worm going on today, I couldn't reach any website. I couldn't reach IEEE Explorer. I couldn't reach... Did anybody else experience this? Anyway, yeah, you did.
No.
Oh.
I wanted to come back to the question.
Yeah, sure.
Is it just a set of linear equations you can solve?
Fun?
Is it just a set of linear equations?
Absolutely. Yeah, that's it. So I have 16 n-squared samples of these guys. They all happen to correspond to the same value, alpha, let's get intensity level 5. This is the image domain. It's a picture. I take 16 n-squared samples of it. And f of k1, k2 appears in this linear equation in a linear way, right? There's no squares, there's no cross terms, there's none of that. So it's good old linear system of equations for which we already described 50 methods to solve it, right? Last time, QR decomposition, Gaussian elimination pivoting, SVD, LUD, you name it. Gauss-Seidel, it's just infinitely many ways of solving this. So it becomes a linear... Is everybody clear about this? Does everybody understand what the gist of the argument is, or have I lost half of you?
I understand the gist. Can we go over like the system of equations that you found out?
Yeah, sure. So here's my samples, right? And all it is I have a left-hand side, which is, let's say the level crossing that we have is level alpha. It takes the intensity alpha, 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 alpha all the way, and it's a matrix times f of 0, comma 0, da 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 da, f of um, um, 2n, comma 2n, right? And it's an overdetermined linear system of equations, or you apply linear least squares, right? Because you have the yeah. So the dimension of this matrix in this here is what is it? 4n. 2n, yeah, that's right, 4n squared. And the dimension of it in this way is what? 16n squared. So it would be, e to the j 2 pi, and for the first element, 0, 0, if you can show this guy as well. So thank you. So for the first, if I'm multiplying by f of 0, 0, k1 is 0, k2 is 0, so I get e to the j 2 pi 0 times x naught e to the j 2 pi 0 times y naught. And then the next element is e to the j, so let's say the next element is f of 0, comma 1. So then index k1 will be 0, index k2 will be 1, but then I have, again, so this row corresponds to x0, comma y0. The elements in this other second row correspond to x1, comma y1. So the second e to the j 2 pi 0 x1, e to the j 2 pi 0 y1, and it goes, so this goes on and on and on down and here. Is that clear? Is that, yeah. So now times this times that, this times, they're all alpha. And I guess the reason the reason Sue Curtis managed to get a PhD out of this, you said, Jesus Christ, I mean, she was a linear system of equations, how could you get a PhD from it? And the answer is, what? Why did she deserve that? We didn't know whether this thing is going to be give us an answer or not. The determinant of this overdetermined system of equations, it could be singular. But Bezout's theorem essentially guaranteed that if the polynomial you're dealing with is irreducible, then they can't have more than Rs common zeros, and therefore this thing is non-singular. Right? And again, remember, f of x comma y is continuous in x, continuous in y, continuous in x and y. X and y are continuous variables. They're not indices of integers. And so what that means in practice, then what Sue had to do is she had to find the locations of these zero crossings here very, very precisely to, like, I don't know, I can't remember, 20 bits or 16 bits or some insane number of bits, the position of these things, right? In order for her to be able to reconstruct the image back. So this was a classically ill-conditioned problem. Question?
I'm just curious about, I mean, how do you know that there's going to be this many alpha values in some image? I mean, like if you had...
No, alpha is fixed.
Yeah.
It's a height. It's
yeah,
a
I know. So
Mhm.
I'm just saying if you had some... I mean, I could think of an image if you told me to draw one that's like not going to have this number of samples at some constant value. I mean, it seems like you could do that.
It's a contour. Remember, f of x comma y is not a discretized image at all.
So you just pick.
Right.
Okay.
Right. That's why I keep iterating it. X and y are continuous variables, so I can pick them as closely as I want. And besides, I can always, if there's too few contour points for alpha, I just choose beta. This result, it's called zero crossing, but it's essentially one level crossing, right? So the upshot of all of these things was that um, um, is that when you solve this linear system of equations, what you observe in practice, if you can roll up just a little bit, thank you, is that to get reasonable reconstruction, we need to know the location of zero crossings to very high precisions, or else the problem is so ill-conditioned we get garbage out. So in other words, this problem is ill-conditioned. But nevertheless, this was a step forward in the signal processing community, and I'll tell you what the reason is. Because the one-dimensional version of this problem just can't be done. You should take a one-dimensional signal, and if there's and you don't impose any extra constraints, there's no way that you can reconstruct it from its one-level crossings or zero crossings. There's one result that refers to the one-dimensional case. So some of you might be asking, okay, how about the one-dimensional case? Can you reconstruct a 1D signal from one-level crossing? And the answer is that, so what do I mean by that? So this is f of x as a function of x, and it's doing all kinds of things, and I cut it with a threshold. And then I mark the positions at which, wow, God, you need a Hercules to open these. So then I mark the locations at which this guy crosses zero. Oh, okay. So here crosses this threshold alpha. And so this is x0, x1, x2, x3, x4, x5, x6. So in general, if you just assume your signal is band limited, there might not be, in one-dimensional case, there might not be enough zero crossings. And you can understand why. Or enough level crossings. You can understand why, because the level crossings are distinct points. And in 2D, the level crossings are a contour, right? Contour is something that, because we're in continuous space, has infinitely many points on it. Even though it's a little contour, I can just pick points that are really close to each other. It's all mathematical arguments. Numerically, everything falls apart, but mathematically, that's what happens. Go ahead.
Does it matter like how close the zeros you pick are? Because I mean, you can pick them infinitesimally close to each other, right?
It becomes even more ill-conditioned.
Okay.
Right. Remember, I mean, that's the one thing I want you to remember about this course. Well, I want you to remember a lot more about this course, but that's one lesson I want you to walk away from today's lecture and last time's lecture. And that is, a lot of these problems mathematically have been shown to have a unique solution, and you can sample the hell out of the contours and define it with 30 bits precision, and you can go to a Cray computer and solve it and get the answer, but it's an ill-conditioned problem. You make the size of the signal bigger, it falls apart. You make the precision of the samples lower, it falls apart. So there is no binary good-bad. Everything is this well-conditionedness. That's why I spent so much time talking about condition numbers and ill-conditionedness, etc. So you can have a lot of fancy mathematical results, but it doesn't mean it works in practice. And I just saying in Persian, I can't help not say it. The saying in Persian, so you can make a cake, you can bake a cake out of iron, but it doesn't mean you can eat it. You can bake it, but you might not be able to eat it. The same thing here, you can cook up unique reconstruction results everywhere, but when you try then to do it in real life, I mean, Fourier transform magnitude, beautiful theorems that tell us that it's possible. And it is possible for small signals, but it's one of those iron cakes that you can't eat it. It's not practical. It becomes very ill-conditioned. And your job as a signal processor or image processor is always apply algorithms that are well conditioned to the problems that you have at hand. Now, it turns out some of these problems inherently are ill-conditioned, so you're out of luck in some sense. But if your problem is not ill-conditioned, you know, apply algorithms that work. Or sometimes people transform their problem into something, if they find out it's ill-conditioned, is transform into something that's well-conditioned and then solve it. And it happens a lot. It's called regularization techniques. How many people have heard of that? Well, we'll talk about it when we get to image restoration, image enhancement. Is you regularize the problem, you make it well conditioned by adding an additional constraint. It could be smoothness constraint, saying I know my images are smooth, or some constraint that naturally come into the domain that you're solving your problem. And actually, this is really what makes a difference between a successful signal processor and an unsuccessful, is to apply the domain knowledge and the constraints that are intuitive to the problem, so that by the right assumptions, then you can get a reasonable answer. Knowing what assumptions to make to come up with an intelligent solution for a problem and how to tame it is more difficult than the nuts and bolts of, you know, equations and stuff like that. And as you go through your graduate program, I'm sure you develop that intuition. And it's very application specific. So the people in speech have their own set of intuitions of how to make things work, and image processing have another ones, and the video people have another, and computer vision have another, and I'm sure control people have another set of tools to apply to the problem at hand. Okay. So let me just wrap up this 1D case by simply stating the Logan theorem, which applies to 1D, but it's not as general as we would like it. And it goes something like band pass signals that are also band limited. I'm talking about one-dimensional signals. Under certain conditions, can be reconstructed from their level crossings. So, for example, if you have a signal with this kind of a Fourier transform that non-zero from omega naught to omega 1, then it's a bandpass signal. It's not a low pass. See, the problem with 1D is the low pass nature of it. When the signal is low pass, it has a DC component, and when you have the DC component, then you can shift the signal up and cause, you can make the variation on it infinitely slowly, and therefore you can make it have absolutely not enough zero crossings. But when you have the band, intuitively, when you have a bandpass signal, you have high frequencies, and you're sort of intuitively guaranteeing that it crosses, it has enough variations, and therefore those are enough to reconstruct it. And this is a very old result. I think it's 1950s or 1960s. It's not something that was done in the 80s. So the upshot of all these things, and in fact I should have started with the 1D case and then moved to 2D, but I got too excited about Sue Curtis stuff. Now, the upshot of these things is that now, even though, I mean, Curtis's thesis is not really all that bad, even though it was ill-conditioned and all these things, nor was Davis Relevitz, even though the problem was ill-conditioned and they couldn't get it to work. But it opened a new avenue, and the new avenue is what? It's called implicit sampling instead of explicit sampling. And let me explain what I mean by that. Well, when you deal with your classical E120, 123 sampling theorems, what do you have? You have Nyquist or Shannon's or whatever the name they want to. It depends actually if you're talking to Russians or Americans or what culture. But essentially, you sample at equally spaced points in time or in space, and if the signal is band limited, then if you sample fast enough, you can reconstruct it uniquely. Blah 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 blah. But Nyquist sampling, we all know about it, and that's called an explicit sampling. I am telling you, you're going to sample at equally spaced point in time, and you're sampling the amplitude of the signal, right? And mathematically, if you want to get perfect, unique, exact reconstruction, you sample the amplitude at what? With infinite precision, right? Real life, we do it with 8 bits, 2 bits, 10 bits, whatever. But from on paper and pencil, you go to equally spaced point in time and you sample that function or that signal, the amplitude of it with infinite precision. That's explicit. This thing, on the other hand, is implicit. I'm not going at pre-specified points in time or space. Instead, I have pre-specified a level, and I'm finding the position of x at which the signal crosses that level or achieves that level. So this is called an implicit sampling. Okay? So even though Sue Curtis's result wasn't practical, it got us thinking along a new dimension that wasn't there before, which is this is an implicit way of sampling images. And so the natural question that arose was, there's two things. First of all, this is unstable. We're going to know the precision to infinite levels, and it's an implicit sampling. And then at the other extreme, we have Nyquist sampling, where let me backtrack. So in this case, we know the position of the samples of the samples at which the signal achieves a certain level to infinite precision, but the amplitude quantization is 1 bit, right? You're either above alpha or below alpha. Essentially, this map is telling us the points in this plane where you're above alpha or below alpha. You have quantized the amplitude to 1 bit, but you require infinite precision in position. Now you go all the way to Nyquist. There, the number of bits to specify position is essentially 0. You're going at equally spaced point in time. I don't have to tell anyone. But the amplitude quantization is with infinite precision. So you kind of wonder if there's an intermediate scheme in between these two extremes, right? For example, what if instead of cutting this with 1 level crossings, what if we have 4 level crossings, or 10, or 200 level crossings? Does then the position requirements of the samples become more relaxed? Can we get away with less precision in the locations of the positions at which, if we introduce multiple level crossings? Actually, and that was my thesis. It came right after Sue. And the answer is, as you would imagine, yes. If you have multiple level crossings, then you can relax the precision requirements for the location of the samples. So what does that mean? Well, I still have this f of x comma y, and now I'm going to have multiple level crossings. These are the points at which the signal crosses alpha. These are the points at which it crosses beta. And these are the points it crosses gamma. So in fact, you can show is that as the number of levels increases, the position requirements go down. Okay, and that you can have a pretty well conditioned and in the extreme where you have, let's say 256 levels, it's almost as if the requirements for position sampling is so low, it's as if you're quantizing the amplitude to 8 bits. Okay, and yeah.
So when you're doing the positioning of where these level crossings are,
yeah,
do you have to do make a complete circle or whatever shape the contour is? I mean, could you just
no, you're essentially
you could just pick a
samples.
certain part of it?
No, you only need samples of it. You don't need the entire contour.
I know that, but
Uh-huh.
what I'm saying is
If there were a circle, say look at that red line you have. It's like
Yeah.
a circular wiggle.
Yeah.
Could you just take the number of values you need off of part of it, or do you try to equally spread them out over that whole contour?
Again, there's a theoretical answer and then there's a practical answer that gives you well-conditioned answers, right? Theoretically, I can pick it all from here. But from a practical point of view, again, I ran into ill-conditionedness. In fact, from practicalness point of view, the more I uniformly spread it out, the better off I am. Right? Okay? So, so basically what I came up with in my thesis was really two classes of sampling theorems. One of them is called, uh, uh, let's see, semi-implicit. That's what I called it, I think. And what that talked about was essentially was, look, if you have a two-dimensional band-limited periodic signal, and if you superimpose periodic lines of slopes that have rational slopes. So you want to have lines of rational rational slopes. That means integer over integer slopes. Then essentially when you superimpose it on top of f of x comma y, and remember f of x comma y is periodic, so these lines wrap around and come back. Or if I have a line of slope 2, it would go boom, come back down, boom, come back down, boom, come back up. And then this wraps around this point. So if you have, this is lines of, for example, this is a line of slope 2, this is a line of slope 1, you can have line of slope 1/2, 2/3, whatever. So if you, what I showed was that if you start with f of x comma y, in general, it's a two-dimensional polynomial. In general, random samplings of it might not result in its unique reconstruction. Yeah, I think that's the key point that maybe I didn't emphasize earlier, is that this linear system of equations, because it's a two-dimensional polynomial, generally speaking, there's no results in two-dimensional polynomial theory that tells you any n-squared samples of this polynomial can result in its unique reconstruction. This is really why Curtis deserved the thesis, is because she applied the Zeus theorem to make sure that, in fact, you can invert this. This is not a singular thing, because the 2D result doesn't exist. The 1D, it does. You have a polynomial of degree n, sample it at any n arbitrary points. You're guaranteed to reconstruct the coefficients, because the matrix you end up inverting is Van der Waals. Everything is good in 1D. In 2D, it's not. And in Curtis's case, it was the Bezoos theorem that rescued the day and made the day. Here, in my case, I came up with conditions. I said, look, if you put your samples on these lines of rational slopes, and if you pick the right number of samples on the right slope lines, again, then you can be guaranteed that this linear system of equations will not have zero determinant. It will not be it will be invertible, and it will be all good. And indeed, so that worked out very well. So what I did is kind of superimposed these lines of rational slopes on top of this, and my sampling points was the intersections of these lines of rational slopes with my with my contours. That's how I pick my samples, right? And in fact, this results in very well conditioned kind of reconstructions. And then the second class of techniques that I came up with was just completely implicit, which basically is another result from algebraic geometry, which says even though a random sampling of these might not guarantee that the determinant of this reconstruction matrix is non-zero, for most times, the number of times it is bad determinant is zero is of measure zero, essentially. So that applies algebraic geometry type arguments. Anyway, so the upshot is you started with the ill-conditioned problem, one level crossing, and now you added multiple level crossings and came up with sampling techniques that allows you to reconstruct these things. So the upshot is that, as I said, we have this spectrum of sampling techniques. So spectrum of sampling techniques that at one end you have zero crossings, or one level crossing, if you will. And here we need lots of position precision, but no amplitude precision. And at this other extreme, like you got Nyquist, as I said, you have no position precision needed, but lots of amplitude. And this thing kind of spans. Here you can come up with this technique here. You can trade off essentially the position accuracy against amplitude accuracy. Why amplitude accuracy? Because if I have n levels, the number of amplitude bits I have to specify is log 2 of n, right? So n levels corresponds log 2 of n bits of amplitude. Okay? And by the way, this trade-off between position and amplitude uh, um, precision occurs in lots of other fields in a different kind of ways. Can anybody think of another example? Real life examples, real life practical situation. Do we have like a circuit students, IC students in this class? Wow, that's too bad. How many of you have heard of sigma deltas? Good, okay. So sigma deltas, is an A to D sampling technique, is a classic case where you're sampling, we're trading off precision and we're trading off amplitude precision in the amplitude against the precision in position. So the way it works is you have a signal, a band limited signal to, let's say, bandwidth omega naught or something. You oversample it by a factor of 100 or 1,000, but you only quantize it to 1 bit. Of course, there's a feedback loop, and you do all kinds of other fancy things. So you have reduced the amplitude resolution to 1 bit, but you've increased the sampling frequency to 1,000 times the Nyquist frequency. And you can show and you build these feedback loops, and you can show that you can, from the 1 bit stream of ones and zeros coming out, then you can apply DSP techniques to reconstruct the amplitude of the signal at the Nyquist rate. Okay, so from one kind of sampling, you went and got another kind of sampling. All right. And the beauty of sigma deltas, if you talk to Paul Gray or the guys who build A to Ds, the sigma deltas have extremely linear properties. Input-output is very linear. Generally speaking, when you build an A to D, like the traditional technique is, you have a resistive network, and you apply. Let me just do a quick contour detour. So A to D is the way they work is you have VCC, and then you have resistive networks so there's a voltage incoming in, and there's a bunch of reference voltages here that have been generated. And let's say this is the ground. Okay, so you have a bunch of reference voltages. So you compare your voltage against this in order to figure out what value this voltage is, and therefore how many bits. If you had eight voltages, you compare them, and you come up with a 3-bit representation of this voltage. Now the problem with this traditional approach of making A to Ds is that the values of these resistors have to be fabricated to be exactly equal to each other, right? And most times after fabrication, they're not. And so how do people do that? It's called post-fabrication calibration. They take a laser and they trim it. They trim them so that they're exactly equal. The more equal they are, the more linear your A to D is. And what do I mean by the more linear it is? This is voltage in, voltage out. You want all the A to Ds have this staircase kind of a characteristic. You want that to be a straight line. You don't want it to be curved. You don't want it to have other bad things, etc. Now, the beauty of sigma deltas is that inherently, by construction, they give you an input-output characteristic that's a straight line, and people are excited. And the idea behind sigma deltas is again the same thing: is you trade off sampling rates against amplitude of the signal that you're sampling. So you quantize the amplitude to 1 bit, but then you oversample by a large factor. And the larger the factor is, the more precisely you can reconstruct the signal at the Nyquist rate, its amplitude. The more bits you get in amplitude precision, the more you oversample in the time domain. So it's a pretty nice application. So you can think about this whole field as kind of binary signal processing. All right, you've quantized this to a black and white image, above threshold, below threshold. And yet another example of binary signal processing is is in lithography, lithography step of IC manufacturing. And you have a mask, as I said, you project it onto the wafer. The mask is binary. It blocks light some places and it doesn't some other places. But the image on the wafer is not binary. It's a gray level image. And many times you have the pattern that you get on the wafer is very different from the mask you put on there. If you wanted your mask, for example, if you wanted to have an L-shaped pattern on your wafer, you make a mask that's L-shaped, but then what you get on the wafer is, this blobby looking, nice, not so nice looking thing. I mean, it's approximately L-shaped, but not really what you wanted. So there's an interesting inverse problem in binary signal processing where you say, okay, like, this is my desired pattern. I know it's tough to get. And why do you think the pattern that you get is rounded like this? Because it went through an optical system that acted kind of like a low-pass filter, although not quite. The optical system, as I said, can be modeled by, partial coherence equations derived by Hopkins that are complicated to compute, and you can apply SVDs to those to compute them fast, but that's a separate story. So you want the red is a desired pattern, and you want to solve the inverse problem, and you ask yourself, what mask, what binary mask? It can't be gray level. The mask is either there or not. You either block light or you don't. What binary mask do I design so that I get this desired pattern on the wafer? And it turns out the answer is you've got to add serifs and jags here and jags there, etc., etc. And this is called OPC, optical proximity correction. Okay, and in the 90s, I was very active in that field. I had a student, Nick Cobb, who is now at Mentor Graphics, who did a thesis on this. So it's solving kind of an inverse signal processing problem. It had huge implications in the semiconductor industry, and I had the misfortune of, like, in 2 weeks I'm going to the same conference, SPIE conference on lithography, and every time people see me, they start complaining and say, "Oh, ever since we invented OPC, God, our masks are so complicated. Our layout designs are now into gigabytes. Thanks to you, we have to deal with really large file sizes." And I guess I have to remind them, you also get better patterns on your wafer. I didn't just destruct your industry or anything, but it's a necessary evil in order to that's how you actually shrink and go into smaller micron sizes. Like, let's say, 20 nanometers or 25 nanometers, etc. Because if you don't take care of these rounding effects, then you can't really effectively downscale into small values, small micron values. Okay, I think that's what I'm gonna. That's the end of reconstruction stuff. Let me kind of pause for a second. Are there any questions or comments? Okay, I'm gonna now move on and do a quick kind of contour and review into Z-transform, and then immediately subsequently after that into two-dimensional difference equations. I think that's the next chapter in Eennlb's book. So I won't get too much. The parts of Eennlb's book that we're going to skip are stability results. I think they're not powerful enough to make them useful in practice, and I think because you see, difference equations and PDEs and stuff have a lot of applications in computer vision and image processing. For example, Perono and Malak here in Berkeley in the 80s, late 80s, early 90s came up with using partial differential equations to both denoise images and also what was the exact problem they were trying. It has to do with something like texture segmentation. So they used these kind of techniques and PDEs and difference equations and to solve that. So I think it's important to talk about computational orders of PDEs and stuff like that, but we won't talk about stability results because I just think that they don't have enough applications to justify time spent And we have so many other interesting topics like image video compression and other things to talk about. So let me start with the 2D Z transform. It's not that different from 1D. There's not too much to it. I'll try to emphasize the differences between 1D. So you have the 2D Z transform of a signal x of n1 and n2, z1 minus n1, z2 minus n2, summed over n1 and n2. And this is again related to two-dimensional Fourier transform in that two-dimensional discrete time Fourier transform of x, which we always denote by x of omega 1 and omega 2, is just x of z1 and z2, but evaluated at the unit circle. z1 e to the j omega 1, z2 e to the j omega 2. So now we have two unit circles. So this, you call this thing unit bicircle. So there's two of them. And similar to the one-dimensional case, we have, every time you have a summation going on from minus infinity essentially to plus infinity, you have to worry about convergence issues. So the question is, for what values of z1 and z2 does this function converge? Okay. In 1D, the region of convergence of x of z depends on r. So if I write z as r e to the j omega, so in 1D, our region of convergence only depends on r and not omega. Okay. In 2D, the region of convergence depends on r1 and r2. Okay. So let me just quickly give you some examples of this. If you can roll up, please. So suppose I have x of n1 and n2 as a to the n1, b to the n2, u of n1, comma n2. Then the z transform is summation a to the n1, b to the n2, z1 to the minus n1, z2 to the minus n2. And you can separate these two summations, make one as a function of n1, one as a function of n2, and what you get is 1 over 1 minus b z2 inverse. But that's only true if magnitude of z2 is larger than b. And then the other summation is 1 over 1 minus a z inverse, but that's only true if z1 is larger than a. So this is it. This is the z transform with these regions of convergence. These two. Yes, please.
What notation did you use to rewrite that, the x of n1 and n2? Is that like a to the n1 power and b to the n2 power?
Yeah, I'm assuming I have a signal of that form.
And what's that u?
Oh, the u. Okay, sorry. That's my fault, because in the first lecture I skipped the part naming my signals. U is a step function, which is 1 here and 0 here. It's making it a right. It's making this signal what's called a first quadrant signal. It's only non-zero in the first quadrant of n1 and 2 plane. Like you have this u of n in one dimension, which is a step function. It's equal to 1 for n larger than 0. And okay, thank you for reminding me. Okay, so is that clear to most people how we got through this thing? Yeah, or am I going too fast? So what it is this is a summation, just like the one-dimensional case with infinite number of terms in it. And if I have a summation, let me just, I skipped a step here. Let me just write down in small form what this intermediate step was. This was summation here. I have summation from n2 equals 0 to infinity of bn2 z2 to the power of minus n2 times summation over n1 from 0 into infinity of a to the n1 z1 to the power of n1. Right? I divide this double summation this into products of two things. This guy is only a function of n2, this is a function of n1. And I'm saying this summation here corresponds to this, provided z2 is larger than b. And this summation is equal to that, provided magnitude of z1 is larger than a. Otherwise, this summation, this geometric sum, ain't going to converge. Right? Every time you have a geometric sum, it converges if the ratio between successive terms is less than 1, right? So this is really the convergence conditions for that. So therefore, ROC means region of convergence. Region of convergence for this Z transform are those values, right? So pictorially, the region of convergence, if you can roll up just a little bit. So pictorially, the region of convergence, if I were to plot in the magnitude Z1, magnitude Z2 plane, is what? It's Z2 larger than B and Z1 larger than A. This is A. This is B. So the region of convergence is this. Okay? And many times, for reasons that becomes clear in just a second, people plot this region of convergence as log of magnitude of Z1 and log of magnitude of Z2. I'll explain that in just a second. Okay, did everybody follow this little discussion?
I follow it, but
Hmm.
it just seems very arbitrary how you just defined, how you wrote x in that way, where you wrote it as a to the n1, b to the n2. I mean, why do that? Like,
To be able to compute this sum.
so you just write it like that just so you can.
I skipped a step in the middle just to clarify how I went from here to here. My goal is to compute the Z transform. And by the way, I mean, this is something I skipped. I always do that when I teach 123. Why bother about Z transform? What's our motivation even bothering about Z transform? Anybody? Do I have any like 123 students? Okay, why bother with Z transform? Yeah, good.
Not all signals have Fourier transform.
Right on. Exactly. Because not these are all tools. Fourier transform, Z transform, they're all tools. The same way as when you're fixing your bike, you have a bag of tools. There's a screwdriver. There's I don't know their names in English then. I have all these metal tools. There's a cutter. When you're soldering. These are all various tools to fix your bike. Here are the tools to do signal analysis to design systems. So Z transform and Fourier transform are both tools. Not all signals have Fourier transforms. Does that mean we pack up and go home? The answer is no. They could have Z transform, but Z transform converges and exists for only certain values of Z's. So only for these values of Z's that I've shaded in this region, magnitude of Z1 and Z2 larger than A and B, respectively, does this summation converge and does this Z transform exist. Otherwise, in all these other regions, that's not in region of convergence, this summation blows up. We don't want to deal with things that blow up. That's not a good idea. I was just going to make a joke saying we're not a terrorist, but that's a bad joke today. But this function literally does blow up in these regions, right? So some functions, in general, here's the thing: because Z transform, what page is it? 12. Because Z transform is the Fourier transform. Where did I put my here? Z transform is the Fourier transform evaluated on the unit circle. If the region of convergence of Z transform includes unit by circle, then the Fourier transform also exists. But if the region of convergence doesn't include the unit by circle, that signal doesn't have a Fourier transform, but it has a perfectly legitimate Z transform that we can use to do analysis, build signals, build systems, etc. Is that clear? So, Chris, are you more comfortable with this thing, or do you have one more question? Okay. Actually, in this course, we won't do too much with the transform. I have very little stuff to say about it, and then we quickly move on to difference equations. Okay, so Again, just to get a review of that, you're welcome to watch the E123 lectures online on the Z transform. That gives a quick refresher of what the various things are. So I want to talk about first quadrant, second quadrant, third quadrant, and fourth quadrant. Um, okay, so first quadrant sequence is a sequence that's non-zero here and zero everywhere else. Second quadrant is here. Third is here. And fourth quadrant is here. Okay? And I'm trying to see if I can, rather than writing this, maybe I can flash the typed up lecture notes. Yeah. Yeah, why don't, instead of me writing, why don't I just flash this? No, you know what? Students always hate it when I do that. Let me just explain it rather than just... It's easier for me, but you know, it's only the 20th time I teach this course, so of course it's easier for me to do it that way. It's better to explain it real time. Okay, so there's one thing I want to, four related things, but essentially all of them reduced to one thing that you need to know about regional convergences for two-dimensional signals, and that is, if I have a first quadrant signal, that means a signal whose region of support is only in the first quadrant, it's only non-zero here. And the same thing can be repeated by second, third, and fourth as well. Then, if I have a first quadrant signal, then, this is not an example, then the region of convergence is going to be something like this. Magnitude of Z1, magnitude of Z2. What does that mean? That means that if a point Z1 prime, comma Z2 prime magnitude is in ROC, then all Z1s whose magnitude is larger than Z1 prime and all and whose Z2 is larger than Z2 prime will also be in ROC. That means if any point is, if this point is in ROC, then everything that above it, to the right of it, above and right of it is also in ROC. That's what this diagram means. I draw it like that, but the meaning of it is this mathematical thing. So if I have a first quadrant signal, the ROC looks something like that. And this was clearly shown in the example we just did. Right? This example, this was a first quadrant signal. It was because I multiplied it by u of n1 and n2, which is a step function here, it's 1 here, 0 here, that made this signal to be a first quadrant signal. And the region of convergence for that, as we saw on page 14, was like that. It's not an accident. All first quadrant signals have ROCs that look like that.
Excuse me, question?
Yeah.
The ROC is a sphere, right?
Yeah, it's not... Because I'm dealing with magnitude of Z1 and magnitude of Z.
Exactly.
So in the essentially Z1 Z2 plane is a four-dimensional space now. So it's a manifold there, and unfortunately it's very hard to visualize or show it, etc.
Is the unit circle just the dot there?
Yeah,
Okay.
that's it. That's it. The unit bicircle, right. And now, because my shoulder is really hurting now, I'm just going to cheat and show the same result holds for second quadrant, third quadrant, and fourth quadrant. So let's just cheat. Zoom in. For second, third, and fourth quadrant sequences, we have this. If the sequence is second quadrant, the ROC is going to be like this. It'll have a point, and all the points above it and to the left of it are in the ROC. If you have a third quadrant support sequence, that is non-zero here, the ROC will be looking like this. If a point is here on it, then everything to the left and below it is also an ROC. And if you have a fourth quadrant sequence like this, then the ROC would look like this, which means if a point z1 prime and z2 prime is in it, then everything to the right and to the below of it is in the region of convergence. Okay? So, zoom out, please. So I can say ditto for second, third, and fourth quadrant sequences. And let me draw that because I think it's good for you to see it. So if I have a second quadrant signal n1 and 2 that's non-zero here, then the ROC will be magnitude of z1, magnitude of z2. It'll be this, this, this. Right? Third, the ROC would be magnitude of z1, magnitude of z2. And if it is fourth, the ROC would be okay. And of course, you can prove yourself that these are true by coming up with other examples. I'm not going to go over it in detail, but for example, just as when you go home, do this as an exercise. X of n1 and n2 is minus a n1, b n2, u of minus n1 minus 1, comma n2 minus 1. That is a second quadrant sequence. And go ahead and do the summation for it, and you can derive the z transform and showing that in fact it looks like it'll have a ROC that looks like this. Okay, I think I gotta stop now. For one thing, I ran out of page numbers on my pages. So that's really time to stop. So I'll see you all on Wednesday. And do get started early on this homework number 2 because it's a MATLAB exercise. And if you haven't written like fancy programs in MATLAB, it could take some time. So don't leave it to the night before.